Welcome back. So we've already looked at at least an iterative method for approaching some of these problems, and that was for finding an eigenvalue. And in fact, if you look at the PDF notes with this class, you'll see that we can find the largest eigenvalue and the second largest, as we talked about, but there's a variation that essentially follows the same approach and enables you to find all of the eigenvalues of a large system using an iterative method instead of direct computation. And this is often very desirable. So now we're going to look at a method for solving this problem in an iterative manner. So we have R m by n, and in general this is going to cost order m n squared to solve, which can be pretty expensive. If we, this costs om n squared. So solving this system directly, the system ATA x tilde is equal to ATY will cost n cubed operations. So, for an example, suppose we had an MRI, and an MRI provides a projection or a look at underlying structure and materials, but not a direct look. That look at the underlying material has been filtered, if you will, through a linear system defined by A, and so we don't get a direct observation of the underlying tissue when we're looking at an MRI, but only its projection. Well, in order to get anything useful, you need a relatively high amount of resolution, and so to solve the inverse problem, you need approximately 10 to the 19th operations to process each MRI image. This is really not feasible in anybody's book. Certainly it would take too long. So for such a system, we need a better way to find a solution. Okay, so the way we're going to approach this is we will recast the problem as an optimization. And when I first do this, ATAX ATY, we'll first simplify our notation just a bit. We'll call that H. We'll call this B. And then of course we have our X. So we have HX equals B. And we know that this is symmetric and positive definite. Okay, it'll become clear in just a minute, but we're going to now define a new type of system. So we define a convex quadratic program as minimizing over x in Rn 1/2 x transpose h x minus x transpose b. Okay, so this isn't the same problem as we have over on the left, but it'll give us another way to approach that problem. And specifically, we can proceed to solve this minimization by setting the derivative to 0. Okay, well, when we take this derivative, we get hx minus b equal to 0, or hx is equal to b. Funny thing that, that's what we had before. So far what we've done is we've taken a problem that is difficult to solve, expressed it as another problem, and found out that we have the same problem. But here's the thing, once we've expressed this quadratic problem, we can now solve that quadratic problem using other methods. And we know that once we have done so, that the solution we get is the same solution that we were seeking, namely the solution to hx equals b. So let's define right now, as a way of understanding this, a one-dimensional example. Like so. In this case, as a function of h or x, we will have our optimal solution x naught right there, and we can do a gradient search. You've probably seen gradient search before, but let's just go through some examples to follow this procedure to kind of orient everybody to the same thing. So we'll have an initial guess. Our initial guess is here on this axis. We'll call it x naught. When we evaluate our function at x naught, we get such and such a term. Now the derivative here is positive because it's increasing as we go to the right. And we want to go back down the hill, so we want to go in the direction of the negative derivative. And so, how far do we go? We don't know yet. So we're going to say x1, our second guess, is going to be x naught minus some step, we're not sure, times and it looks like a running into the other notes. Okay, so we're going to step that direction. So what's going to happen? We have a positive derivative of x at that point. So when we subtract alpha times that, we'll be moving in a negative direction. So x1 is going to be somewhere over here. And we're now closer to the optimal point. And we'll continue this same type of operation as the derivative gets smaller. Since we're moving proportional to the derivative, we won't move as far. So That's the general idea. Now it's possible, if we're not careful, that we could overshoot or undershoot. So for example, if we had the same problem and we had our initial guess right here, and we wanted to move in this direction as defined by the negative derivative, if we move too far, just for illustration, I'm going to put that there. It's not. It's possible that we could move further from our solution instead of closer. So in this case, we have step size too large. And of course, we could have an optimal step size if the world were that nice and wonderful and beautiful. Our optimal step size would take us from this point right down to there. It's a little bit too much to hope. Okay, so this is a general idea. We just want to move in the direction of the negative gradient. In general, we're going to have more dimensions than one, which adds some complicating factors, and we'll deal with a few of those as we go along. So in order to do this, let's start out by defining the error or residual. As Rk is equal to B minus H xk. And we'll call this residual. So, first off, I need to go back and take a look at this other page here. What is the gradient of our 1/2 x transpose hx minus x transpose b? The gradient itself is this. No, I'm sorry, one line up. This, without the 0. Well, not only then is this our error or our residual, but this here is actually minus del of x evaluated at x equals xk. Well, that's exactly what we wanted when we're updating our guesses as to the solution. And so our update equation just becomes x plus 1, x of k plus 1 is equal to x of k minus alpha times our derivative, but we've already got this negative sign in there, so this then becomes a plus alpha k rk. There's our update equation. Okay, that's it. You have enough that we could actually move forward and do our gradient descent. The problem is this alpha. We know if we choose alpha too large, that will actually diverge. If we choose alpha too small, it may take a very long time to converge. And since we're doing this gradient descent because we have large computationally difficult systems, we really would like to choose alpha as best we can. Ideally, we would choose an optimal step size, but that's if we knew the optimal step size, it would imply that we knew the equation. And in fact, if you want more, the Georgia Tech ECE6250 talks about adaptive filters, where we explore all sorts of different options and ways of approaching these problems. And many of them are quite clever and quite effective at arriving at solutions and can be applied in many different ways. We can't go into all of that right now or into all the analysis, but we can do some simple analysis right here that will help us choose our alpha. So we want this to be as small as possible. We're going towards the minimum. And we know that that is actually just equal to xk plus alpha k rk. And we want to solve for the alpha that minimizes this. So anytime we're trying to minimize something, we take a derivative because we have these nice, well-behaved systems here. And that's just equal to derivative of one thing that people often have trouble with is remembering how the rules of calculus apply to matrix systems. And there's a wonderful little guide on matrix calculus that I find very useful, and actually I refer to it typically at least once a year while teaching classes, because it's hard to retain all of this in your memory at once if you're not always driving it or studying it. So I'll post that in the class website. Okay. Well, so we have two vectors here. We have the derivative of f transpose using the chain rule times rk. So we have rk. That's great. And in order to solve this problem, we need rk to be perpendicular to our derivative of our cost function. And therefore, rk plus 1 perpendicular to rk. Just to make sure you followed that last step, remember that this quantity here, the derivative of f evaluated xk plus 1, is equal to hx minus b evaluated at x k plus 1. Well, that's equal to the negative of excuse me, r k plus 1. Well, since it's equal to 0, if something is perpendicular, the negative is also perpendicular. So we drop that and we just say that rk plus 1 has to be perpendicular to rk. Well, now we're getting close to our solution here. So for rk plus 1 transpose rk equals 0, we get b minus h x k plus 1 transpose rk is equal to 0. And let's put in the definition of xk plus 1. So we have b minus h times xk plus alpha k rk transpose rk equals 0. And we can go through a few more steps, but now you can see the rest is just straight up algebra. And we're going to get alpha k is equal to rk transpose rk over rk transpose h rk. So this ensures a rapid convergence. And for most problems, most large problems, it converges in 20 to 50 steps.